Okay, so I think we can start the webinar. I hope I'm audible to everyone in the meeting. So I would like to welcome all participants to this webinar on radio frequency identification systems for unusual applications by Dr. Andrea Michel of the University of Pisa, Italy. So following is the abstract of the webinar. The typical assumptions such as free space propagation and local plane wave illumination cannot be considered to calculate or estimate the performance of passive UHF RFID systems in terms of read range and read rate. This presentation aims at describing some practical applications in which new propagation models must be considered to optimize the antenna and the overall UHF RFID system design. As for example, those unconventional scenarios where the distance between the tag and the reader antenna is smaller than a wavelength. That is, the antennas are near field in the UHF frequency region. So before I formally introduce the speaker, I would like to say a few things about him from my personal experience. I've had the pleasure of meeting Andrea twice, once in URSI AP RASC in New Delhi, which was in 2019, and the second time in conference RFID TA, which was in Pisa, also in 2019. So he is a personification of humility. He has a great sense of humor and is very dedicated to research. And although I've known him for only a couple of years, I hope we can continue to have a good relation for many years to come. So with that, I now move on to the formal introduction of our speaker. Andrea Michel received the BE, ME, and PhD degrees in telecommunications engineering from the University of Pisa, Italy in 2009, 2011, and 2015, respectively. In 2014, he was a visiting scholar with the Electroscience Laboratory, the Ohio State University, Columbus, Ohio, USA, under the supervision of Professor John Volakis. During this period, he was involved in research on a theoretical analysis on the accuracy of a novel technique for deep tissue imaging. Since 2015, he has been a postdoctoral researcher in applied electromagnetism at the Microwave and Radiation Laboratory, Department of Information Engineering, University of Pisa, where he is also currently an assistant professor. He is involved in the design of antennas for automotive applications, MIMO systems, and wearable communication systems, also in collaboration with other research institutes and companies. His current research interests include the design of integrated antenna for communication systems and smart antennas for near-field UHF RFID readers. Dr. Michel was a recipient of the Young Scientist Award from the International Union of Radio Science, URSI, Commission B in 2014, 2015, as well as in 2016. So in 2016, he received the Best Paper honorary mention from the IEEE International Conference on RFID Technology and Applications, Shund, Guangdong, China. He serves as an early career representative for URSI Commission B, Fields and Waves. Okay, so now that all the formalities are over, I would like to request our speaker to kindly start his presentation. Andrea, can you hear me?
Yes, thank you. Thank you very much for your kind invitation, for your kind presentation. I'm trying to share my screen.
Yeah, we can see it.
Okay, fine.
Yeah, we can see
Can you clearly? Can you see presentation?
Yes, we can see it clearly.
Okay, fine. Okay, just 1 second, please.
Yeah, take your time.
Sorry. Okay. Okay, that's good. I cannot see myself in the webcam, so it doesn't matter. I try to do that, but
oh, we can see you clearly as well as the
okay, great. This is the most important thing. Okay, thank you very much, and namaste, ladies and gentlemen. And Thank you, Sayan. It's a pleasure to be with you today. Let's say this morning time and this afternoon Indian time. Today I would like to talk with you and to discuss you about some particular application on RFID, radio frequency identification systems. I call them unusual, unconventional scenarios and applications because this is a little bit different from the typical analysis that we usually carry out on RFID systems. But first of all, as Sayan already mentioned, it's my third conference in India. The first one was in New Delhi, was the URC AP RASC in 2019. It was a very, very nice trip there, 1 week. It was an amazing city, amazing people, and amazing conference as well. And that was the first time I met Sayan. But with Pisa in September 2019, because we organized the IEEE RFID conference, TA, Technology and Applications in Pisa. That time I was the TPG vice chair. You can see here one picture of us, probably Sayan, me, and Dr. Rajat Kumar Singh, who is a postdoc here in our group in Pisa, and probably most of you already know him. I don't know, but for sure you all know Sayan. Okay, thank you again for this introduction, and let's go to the outline of this talk. And I would like to briefly present something about RFID systems, and I want to highlight what I mean for conventional or unconventional scenarios. And we will see together, we will take a look at 3 scenarios where, for example, we cannot far-field region, but we are in the near-field region. One case is a printer encoders. Second case is a smart glove antennas. And the other scenario that I would like to mention at least is the when the tag is not illuminated by the guided waves. So, well, it's not illuminated by a plane wave, but it is a guided wave. So it is in a guided structure, like a waveguide, for example. Okay, and then we can discuss and conclude something, and maybe I hope there are some question and interest from the audience. Okay, let's start. We probably all know about RFID systems, but let's briefly describe these systems. So we have 3 main components. Let's say 2 main components. We have a reader and we have a tag. The reader is connected to the laptop or a computer, and it is connected to a reader antenna. We can have up to 4 reader antennas for fixed readers. But okay, let's consider just one antenna. The reader can interrogate the environment, the surrounding environment, and if there is in this area, in these scenarios, if there is one object with equipped with a smart label, a transponder, a tag, an RFID tag, these mainly passively backscatter the signal back to the reader, and then the tag can send its own identification code. And so you can identify the object without line of sight. You can think about a barcode. Barcode is used for identify objects, for example, to the supermarket or everywhere. and you can scan with a specific device, and you can scan, but you need the line of sight. You need to see the barcode. Our application system are used instead of barcode because they do not need. Probably the main advantage of this system is that you don't need a line of sight. Okay, tag can be embedded inside the box, for example. It can be maybe placed in some particular position with respect to the object. For example, let's think about a T-shirt. Maybe the tag can be applied inside the T-shirt, so we cannot see it. So we have typically we consider two main components. I want to add the third one. The first is the reader and the reader antenna. There are a lot of readers, and we can design a lot of antennas for readers. And depending on the specific scenarios, the specification, the characteristics of the reader antenna can be different. And I'll tell you later. The second component is the tag. The tag is usually attached to an object or to a person, for example, or to an animal, whatever. And typically they are low cost, low profile. They have a different layout. You can search, look for UHF RFID tag on Google, and you can see the images, and you can find a lot of different shape and size of tag. Tag antenna is equipped with a chip, a microchip, which contains the identification code. So when the tag is illuminated by a wave, it collects some energy from this interrogation wave, and part of this is used to activate the chip. The chip, when it is activated, starts to modulate the backscatter signal, the amplitude, the phase, it depends. And then the backscatter signal goes back to the reader antenna and can be detected by the reader. I want to add a third component of these UHF RFID systems, which is the propagation channel, because it is very important also to take into account the shadowing effect, attenuation phenomena, multipath. Multipath fading is one of the most critical aspects, for example, for indoor application. In one room, full of people, full of objects, multipath is very disruptive in some cases. And yes, of course, also material of the object, because for wearable tag, for example, we need to take into account the effect of the biological tissues, for example. Okay, there are a lot of aspects, and it is sometimes it's not easy to take into account all of them, but it is important to know them and to control at least the most important. Where we can find RFIDs? Everywhere. Even if we do not know, but RFID are usually used in supply chain. For example, for the dock doors and for tracking the goods, forklifts to track the position of the forklift and the position of goods or position of pallets along the conveyor belts in a warehouse. Okay, you can think that the reader antenna is somewhere fixed inside the warehouse. The warehouse is very, very big, and you can see and you can detect all the tag, and you can have a real-time inventory. Okay, so this is very useful for logistic applications. But maybe during our journey, for example, at the airport, you know that your luggage, not the carry-on luggage, but all the other are equipped with some labels and with barcodes. And you may find an RFID tag printed inside this paper label attached to your luggage. And this is useful. This is used for tracking the baggage, and but also passenger. For example, our passport, we can identify automatically at the airports by using our passport because of one chip which is embedded inside the passport. That's another application of RFID. In vehicular application, automotive, but also for plane. I've been told that all the components, all the parts of a Boeing 787, but probably also other airplanes, are identified by means of smart label, by RFID tags. So all the components, all the parts of the airplane have a specific identification code, and it is used to control the process when during the fabrication of the airplane. Can you imagine how many components may have one single plane? So how can you control all of them? How can you have a real-time inventory of all these components and parts? But very, very useful is RFID in e-health, safety. Okay, so RFID tags are integrated in scissors, in surgical instruments, but also in blood pipe and drugs, and all these things. And of course, I'm not going to mention that there are also implantable RFID. Under, for example, in the hand, you can implant an RFID, a very small chip. It's a very small chip tag inside the under the epiderm. Retail marketing, supermarkets, all the objects can be equipped with a smart label for real-time inventory. But you may know Decathlon. You can go to a Decathlon shop, and all the goods, all the T-shirts, all the dresses are equipped with a smart label, such as RFID. And fashion industry, because you can also use you can design your tag by means of a textile fabrication process, and your tag with the name of your brand, for example, in order to for aesthetical reason, let's say. Okay, so you are not going to see one antenna, but you can read your brand, for example, or whatever, and but you don't know that it is an antenna and a chip. Sport activities like marathon, and you can see here there is the tag is attached to the ankle of this person, or on the shoes, and maybe it is useful to identify the people during sport activities. Okay, let me mention my favorite one. With a cat door, you can identify the cat. There is an RFID tag to the neck of the cat, and the cat door, let's say, is equipped with a reader antenna. When the cat with its tag is in proximity of this reader antenna, can be identified, and if he is allowed to go in, then the door automatically is unlocked, and he can jump in the house. I have cats, So it's very useful, these systems. It will be very useful, actually. Okay. Those are conventional scenarios. I want to call them conventional scenarios. Why? Because I can study this problem by considering a reader antenna and a tag antenna placed at a distance d. So in this case, we can use the Freeze equation, and we can see which is the power received by the tag given the power transmitted by the reader, given the gain of the transmitted antenna, the gain of the receiver tag, and the lambda, which is the wavelength. For example, at the RFID, the UHF RFID band is around 900 megahertz. It depends on the geographical position, but UHF band is around 900 megahertz, and 4 pi and d, the distance. So the power received by the tag decreases the square of the distance, but the power is needed to activate the chip. If the power received by the tag is higher than the chip sensitivity, then the chip is activated and they can backscatter the signal after modulating. But this is just a forward link. You can consider taking into account also the backscatter signal, and then you can consider the reverse link. And so you may use radar equation. Okay, this is what it is typically do. What is typically done with RFID systems for conventional scenarios. Radar equation, where this parameter is the radar cross-section of the tag. Okay, and so you can see which is the power received back by the reader. And if the received power, the power received by the reader is higher than the reader sensitivity, then the tag can be really detected. But we can use those equations just for under very important hypotheses. So the first one, probably the most important, is the far field region. The two antennas must be placed far enough that for not electrically small antennas, the distance must be higher than 2d squared over lambda, where the capital D is the maximal size of the reader of the antenna. Okay, so if they are placed at those distance, then we are in the far field region. And also, those equations are not taking into account reflections, no multipath, but just free space. This is very nice from a research or academic point of view. This is not the reality. Because in a lot of scenarios, I'm now calling them unconventional, the reader and the tag are not far enough. For example, you can use a smart sales point. There is a computer, and you can find here a reader antenna, and the RFID system is integrated in this device, and you can just put your item equipped with a tag. You can put on it, and it is automatically detected by the system. In that case, the distance between the objects and the reader antenna, the tag and the reader antenna, is a few centimeters or even few millimeters, very close to each other. So definitely this is not far field. So in this case, we cannot use the radar equation because the two antennas are in the near field region. Maybe radiative near field region, but if they are very close to each other, they are in the reactive, so-called reactive near field region. So the characteristics of the antenna in this for this must be different because the reader the gain in the near field region, the gain of the antenna is not even defined. So this is not the key parameter to take into account. We need to take a look on the field distribution, both electric and magnetic fields. And maybe we need to optimize the antenna by shaping the field. And the other unconventional scenario is sometimes the tag is not even illuminated by a locally plane wave. For example, you can see rolls of metal sheet, and sometimes to identify each roll, the tag is placed inside those. And in that case, this is not a plane wave, but this is approximated by a circular waveguide. So we cannot consider a locally plane wave, but a guided structure and a guided mode. So for scenarios, you can think, and there are a lot of them, we need to design ad hoc reader antennas, ad hoc tag antennas, but we need also to take into account specific propagation channel models to estimate the performance of the system. Let's start with just one application, or at least a scenario. This is the near field UHF RFID systems. Desktop reader, smart shelf, item level RFID in retail and pharmaceutical industry. In all those applications, the distance between the tag and the reader is not far enough. So they are close to each other. This is important because you want to detect the tag if you want to pay, for example. You want to pay just for the item you are putting in the device. So you want to detect only the tag in proximity of your reader, and you want to avoid the detection of farther tag. Maybe they are still on the shelves, for example. So how can we do that? Okay, first thing that we can do is to control the power of the reader. We can lower the power, and so we can limit the tag detection. This is, of course, one solution, but this is not the best solution, in my opinion, because in this case, we are not going to shape. We are going to change the amplitude of the field, but we are not to change the field distribution. We are not changing components. We have no control of the polarization of both the electric and magnetic field. We cannot make the field stronger in area instead of others. So, in my opinion, the best thing is to use a specific tag, a specific reader antenna. And so all the reader antennas for near field application must be low cost, scalable, low profile, wideband. And magnetic field should be as uniform as possible, must be strong in a limited volume, and not the gain should be low, because we want to avoid the detection of farther tags. Characteristics are different. So we are not going to talk about radiation pattern. Okay, so there are different key performance, and there are a lot of antennas proposed by scientific literature about near field RFID, UHF RFID, and you can find review of those in one paper I wrote with Professor Zini Chen of Singapore, at the University of Singapore. But I think we can group all those antennas in 4 main groups. So the first one is represented by loop antennas. So in this case, we want to maximize, as expected, we want to maximize the magnetic field. And very famous are the segmented loop antennas. So those structures are loop, but you want also to have you want 2 things. You want to have an antenna big enough because you want to cover one device, and you don't want to maybe a very small device, but you want to cover with a uniform field, like an area of 30 by 40 centimeters. Okay, let's say something like that. This is a typical application. This is due to typical application. But if your loop antenna is the perimeter of your loop antenna is comparable with the wavelength, and at UHF wavelengths are around 30 centimeters or something like that. In that case, your loop is a resonant loop, so the gain is high, and the field distribution has a null of electric field in the center of the antenna. We cannot have nulls in the field distribution, because a null of electric fields means that you are not going to detect the tag when it is placed in this device. Has a maximum uniform field, magnetic field, and in the center of the structure. So segmented loop antennas has been proposed 15 years ago, something like that. And the idea is to load the loop, which is physically large, with some capacitors, lumped elements or distributed elements, it doesn't matter, but they are capacitors along the loop to keep the current in phase, to keep the current phase constant along the loop. So this is a physically large, but it is an electrically small loop. In this way, we can generate a very strong field and well uniform and around the antenna. And this is there are a lot of version: single loop, multiple loop, dual loop, different. So the first group is represented by loop antennas. The second group is represented by leaky transmission line antennas. Basically, they are not real antennas. They are bad transmission lines. You can use microstrip technology, coplanar waveguide, coplanar strip line technology. And the idea is to have a meandered transmission line, which is a leaky transmission line. So it's, and at the end, the termination is a loaded, matched load at the end of this transmission line. So in order to avoid the generation of the reflected current, and then we can avoid the generation of stationary current, and then a stationary electric field distribution and magnetic field as well. So this is more or less the idea, and the transmission line can be shaped properly. You can see here in the picture there is one antenna, but I can show you also in my hand. I hope you can see, because I cannot see myself, but I hope that maybe you can see one prototype and the other prototype, and because we designed them a few years ago. Okay, third group are resonant antennas and arrays. In this case, we are going to use antennas, resonant antennas, but maybe an array where the power is split in all the antennas. So antenna is resonant, but it is fed by a low power. So in this case, we can a little bit shape the field. But for example, in this group, there are near field focused array. So there is a distribution of antennas, array of antennas, but the phase of each element is properly set in order to focus the field, the electric field, for example, in one specific spot, and maybe not far, but in the near field region. And the last one is the modular antennas, which is basically a combination of the other antennas. For example, I want to show you this a possible layout, which consists in a traveling wave antenna and a low gain resonating antenna. We published something about this, but let me show you this structure. And you can see that there is the port is in the center of the structure, and then we have a spiral transmission line. This is a microstrip transmission line. This is not a real spiral antenna, because this is a microstrip. There is a ground below it. So it is not radiating too much, but it is a leaky transmission line. So it is helpful to generate a field at least uniform in this area. So there is a switch at the end of this transmission line. You can, it is an absorptive switch. You can use a matched low 50 ohm resistor, and then you have a field concentrated in this area. You can switch the RF switch. I'm sorry for the repetition, and you can activate the 4 resonant slot antennas. There is a delay and matching network. We can split in a quarter of the power to feed the first, a quarter to feed the second, and that's it. We can get a 90-degree phase shift of the current, so we can have a circular polarization. And in this way, we can change the field distribution. How? If you set the switch in order to have a matched load, you are going to generate a field strong enough in the center. And maybe it is helpful when your tag is placed on the reader antenna. But you can switch the state of your RF switch, and you can fit the 4 resonant carved slots, and you can increase the field distribution and then the read range. For example, in this animation, there is it is the electric field distribution in a transverse plane. You can see here the antenna profile. And for the first state, of course, the field is, the color bar is the same. And but the field, in the first case, the field is concentrated in a very proximity of the reader antenna surface. And in this way, you can confine the read range. But you can activate the 4 slot, and you can extend the field distribution up to whatever. Okay, so this is what I mean when I say with the same amount of power, we can change the field distribution. For example, for this antenna, we fabricate a prototype in collaboration with the University of Oviedo in Spain, and specifically with the Professor Marcos Rodriguez Pino. We tested, you can see here the prototype, and you can see the near field electric probe, and the comparison between the simulated and the meshed electric field. There is a quite good agreement. But let me go at the next slide, because remember that this is not important. It's not important just to design an antenna, but it is important also to have a high level measurement, okay, system level measurement. So it is important also to test an antenna in a real scenario with real tags. So for this reason, we used those tags. For example, dipole-like tags. We create a grid, and we tested the tag detection in each of these 64 cells, 8 by 8, around above the antenna surface, and by varying the distance. We used this reader. It's a commercial reader from one Italian company. And you can see the results here. So when only the spiral structure is activated, the read range, the green means detected, green cells are detected tags, red cells are undetected tags. And you can see that when the spiral traveling wave antenna configuration is activated, the tag can be detected up to 10 centimeters, let's say. But if we change the state, and we can activate the carved slots, we can extend up to 60, 70 centimeters for both tag orientation. How can we study this? What is the equivalent equation of a radar equation or a freeze equation. We are in the near field, we cannot talk about radiation patterns, right? Okay, so our idea is to estimate the power received by the tag, I mean just the forward link, and see this system composed by the reader antenna, the tag antenna, and the propagation channel. And we can simulate it, and we can collect and consider as an impedance matrix. Then the tag antenna is loaded with a chip, and we have from datasheet the input impedance of the chip. And then we have the reader equivalent circuit at the left side. So we do want to estimate this power transmitted from the reader to the tag, also from simulation. Of course, we want to predict the performance of the system before prototyping. Okay, so in simulation we can have the reader antenna. You can see here the CST model and the tag, and we have 2 ports. And then we can vary the orientation, the position of the tag with respect to the reader antenna. And we can, for each position and orientation, we can extract the 2x2 Z matrix. And we can use it in an equivalent circuit to compute one new figure of merit, which is the power transfer efficiency. The power transfer efficiency is defined as the ratio between the power received by the tag and the power emitted by the reader. And we can compute it in terms of Z parameters. So once we collect the Z parameters, the matrix, we can compute the power transmission efficiency distribution, and maybe we can compare it with a simulated RSSI distribution, which is a figure of merit of the detection of the tag. Let me show you that. You can see that there is a very good agreement, let's say, between the distribution of first line. We have the first state spiral transmission traveling wave antenna. The second line is the state 2, with also the resonant curved slot antennas are excited. First column, we have the simulated electric field distribution in one plane at 10 centimeters from the antenna surface. The second column is the measured electric field with one probe, homemade probe that we fabricate in collaboration with the University of Oviedo in Spain. The third column is the computed power transfer efficiency distribution. So given the CST simulation, we extract the Z matrix and we compute the PTE for each position, and we can interpolate and we can get a map, a color map. And the fourth column is the measured RSSI distribution. RSSI means received signal strength indicator. This is the power received back by the reader antenna after the backscattering of the tag. And you can see there is a good agreement. So for the 2 states and for different orientation of the tag and for different tag as well, because we can change also the tag easily. And for example, by simulation, we can choose the specific tag layout, for example, for our system. And we can predict the detection of the tag. For example, if there are some nulls of detection somewhere, we can change the design of the reader antenna and make the generated electric field more uniform. So we think that this is not the real equivalent parameter or the equivalent to the radar equation, but I think that it is a good figure of merit to take into account during the design and of the UHF RFID system and specifically the reader antenna. Okay, I want to say few words about one specific case of near field application, which is the printer encoders. All the tags must be encoded first. So we need to write some information on it, okay? And informations can be encoded by using this device. And where there is a reader antenna, an encoder antenna like this, and there is a set of tags. Tags are typically placed on a roll like this, each other. So each tag is attached to an adhesive label, and the pitch is the distance between the two tags. Pitch is typically few centimeters, maybe 2 centimeters. It depends on the size of each smart label. But you can see that you can think that those labels are placed on this conveyor belt, and at a few millimeters, like or even less, there is the reader antenna. So the reader and the tag are few millimeters, so very close to each other. This is a reactive near field region. And the reader must encode information just on the tag above it. Okay, and not, we need to avoid the encoding of the tag placed close to the target tag. Okay, so there are other tags close to each other, but we want to encode just one at a time. So this means that the printer encoder antenna must be specially selected. Okay, so we need to design the antenna to make the electric field distribution as spatially selective as possible. And in this case, again, we cannot use typical gain, bandwidth, half power beamwidth, but we need new figure of merit. Okay, so again here we tried to use different antenna for readers, and you can see here Zirlin is the antenna designer from Zebra Technology, who proposed this structure, which is actually integrated in the commercial Zebra printer encoders. So this is a commercial reader, and we try to change, and we are still working on that, changing the specific, the optimal reader antenna, encoder antenna design layout to make this antenna as spatially selective as possible. But to study this problem, we are again using this equivalent model for the power transfer efficiency. Okay, I'm not going to give more details because time is running, and so. But if you have any other question about this, we can discuss, of course. Okay, I want to say something about another scenarios, which is smart gloves. Together with Dr. Singh, we are working on smart glove wearable antennas. You can see that in this era of Internet of Things, there are a lot of wearable devices. We all have our smartphone. Funny application, you can use your smartphone equipped with some microphone, and you can use your finger to call because there is a Bluetooth connection to our smartphone. So the glove is a part. Oh, and of course, so for reliability purposes, there are also mechanical structures and sensors integrated in the smart glove. So, a smart glove for UHF RFID systems is one glove used to detect the tags. So one operator can use this smart glove and can grab some objects with the tag, and the tag can be automatically detected. For example, I want to show you one prototype. So you can see that this is this glove, and we have an antenna layout integrated on the back of the hand. And maybe you can think to connect this glove to a wearable reader. There are some readers, for example, you can see this, and this is not a watch, but this is a RFID reader. This is wearable, and you can think to wear it like this. And you can think to integrate this reader in your smart glove. Okay, you can create a connection between the reader and the textile antenna, and so you can create your smart glove. You can automatically detect the tags. Again, this is a near field application, because you want to detect just one tag close to your hand. Okay, so you're not going to scan all the environment, surrounding environment. So I told you the goal. So we have the wearable reader, we have the reader antenna, and we can detect the item, the tagged item. So main characteristics I already said, but the reader, of course, we can choose, given the size and given the application, we can choose our specific layout for the reader antenna. In this case, we want to focus the field, because of the applications, we want to focus the field along the fingertips. And at the same time, we want to limit the radiation back toward the human arm, because it's a waste of energy. We want to focus the field where the target item is supposed to be. And we want to limit the exposure, the waste and the exposure of the human tissue to the electromagnetic fields. Okay, so for this reason, Dr. Singh designed this proposed this Yagi-like antenna, and you can see the one port. Okay, this is exactly what I have on my hand now. There is a one port, there is this folded dipole, this is a fed dipole, and then we have two directors. All the directors are folded because of the size to make the antenna as compact as possible. And to feed the antenna, we need a balloon. We have a snap button to connect because we need to solder the cable. Okay, we need to solder the coaxial cable and the balloon to the antenna, but we cannot solder direct material because it's also textile material. So we are going to burn the tissue, and not the biological tissue, but the cloths. Okay. So we need a snap button to connect and to solder it. So this is a focus on the 3D material, because we used a 3D fabric, and which are 3D printed. We have two prototypes. We evaluate a B-elastic 3D conductive fabric, which has a good resistivity, but unfortunately, this is a 3D and it is thicker. The structure is thicker and might be not easy to be integrated in a smart glove. And the second material we consider is a quadrilastic plane. And this is thin. It's not as thick as the first, but the resistivity is a little bit higher. And so more losses, but as a trade-off, given the application, okay, we fabricate with the second device. But there is a good agreement with the simulation and measurement results in terms of reflection coefficient, During the design, we considered, and we need to do that for wearable application, we considered even a simplified equivalent model of the human hand, skin, fat, muscles, bones. They are all dielectric materials. You can find their dielectric permittivity and loss tangents at around the UHF RFID band. They depends on the frequency, as we can imagine, and so the design of the antenna must take into account, because the hand has a load effect on the resonant antenna. And since it is a wearable antenna, it's also important to test the variation of the performance by varying the hand position, when the hand is completely open, when it is closed, when it is partially closed. But it seems to be robust. Okay, this is also because we integrate the antenna on the back of the hand. Other thing would be if the antenna would be integrated, for example, on the palm of the hand. This is an area which is more subject to variation, mechanical variation, okay, and stretching and bending. So how can we test it? We may see the radiation pattern of that there is a slight focus along this direction, which is the fingertip direction. But wait, again, is it radiation pattern important for this kind of application? Think about this application. You have your hand, you have an object, you want to hand this object. Maybe the distance is less than 34 centimeters, which is the wavelength at 867 megahertz, which is the European UHF RFID band. So if the distance is lower than lambda, we are in the near field region. So we cannot use gain and radiation pattern to analyze the system. And we cannot use the radar equation again, but we need to new figure of merit. And again, we use the power transfer efficiency. So this time we consider the Z matrix. In the Z matrix, we consider the hand, the propagation channel, and the object, and also by varying the orientation and the distance between them. And this is a 2x2 impedance matrix. We extract those values and use to compute the power transfer efficiency again. I already said that this is not sufficient to fully predict the tag detection, because you can see here, this is the power level from at the reader. We can transmit the power. There is a path loss given the distance d of the forward link, and we have a power incident on the tag. Part of this power is used to activate the chip. Part of the power is used to modulate back the back signal, so we have a loss of power. Then again, we have the path loss, same path loss of the forward link, and going back to the reader, we have the power received by the reader. So I'm saying that the power transfer efficiency can be used to estimate this path loss, this loss of power between the reader antenna and the tag. We are not taking into account modulation losses and other losses due to the material. The tag is the material of the object the tag is attached to. We're not to take into account multipath effect and so on. So this is a qualitative estimation that's to see if the tag can be activated. But again, we test it as a function of the distance between the hand and the tag, and we compare the power transfer distribution, the power transfer efficiency, and the power received by the tag by simulation, and with the received signal strength, the measured received signal strength. So there is a quite agreement, okay, between those two curves. At least we can see that on front, along the fingertips at the same distance, we can have a higher power received by the tag. So the read range can be higher along the fingertips. Just to mention that we also set the maximum power for measurement on the basis of the specific absorption ratio of the hand. Okay, the SAR simulation by CST. So okay, this is a limit to respect of the biological tissue interaction. And you can find more details on papers recently published. Okay, I think it is 55 minutes, so I have 5 minutes left. Let me just, sometimes this is not, sometimes the distance is not the big problem. We are, until now, I showed you some application where the main problem is the distance between the tag and the reader antenna. Okay, so in that case, we can change the equation to study the system. Sometimes the problem is the propagation, because in there's like drip pipes, metal drip pipes, or roll of metal sheets. Like for example, this is a roll of Tetra Pak, where maybe we have a Tetra Pak brick in our homes, and underground tunnels, or even heating and ventilation and air conditioning pipes, metal pipes. Okay, if the tag is placed inside those metal pipes, we need to change the propagation, because this is not a plane wave. This is a guided structure. It can be approximated with a circular or rectangular waveguide. So in that case, we need to create a different model for signal propagation. We cannot use a radar or freeze equation. So let me go. So that's the new forward path. We have this is a schematic representation of this structure. We have a metal pipe with a tag inside somewhere at a certain distance from the aperture. So we have a reader antenna, whatever it is, and which is connected to the reader. So we have the transmitted power, we have the reader antenna. Okay, we are not going to, this is very close to the aperture of the metal pipe. Can you imagine from a real point of view? Okay, the distance is not so far. So again, we cannot use a gain or a directivity between the power transmitted by the reader and the power at the aperture of the metal pipe approximated by a circular waveguide. But there is a coupling coefficient between the reader antenna and the guided structure. And depending on the size of the metal pipe, we don't know which mode is propagating, because we can have propagating modes inside a waveguide. But depending on the size, we can have a cutoff, and maybe we can have just one mode, for example. This coupling is something related to both the field distribution of the mode at the mode of the reader antenna side, and the modes distribution on the metal pipe aperture. Then we have at distance d, we may have some attenuation of the signal due to the propagation inside the metal pipe, this metal pipe. Then we have a tag, and there is a coupling now between the tag and a mode, a specific mode. I call it SN tag, which is the mode, the end mode, propagating mode inside the metal pipe. And then the coupling between the power transfer efficiency the coupling coefficient between the tag antenna and the chip as well. So at the end of the day, we can have the power received by the tag, and also the reverse path, the backward, again from the tag, we have some power, again attenuation due to the non-perfect, non-ideal metal pipe, and the coupling between the propagating modes and the reader antenna, and then the power received by the reader. And in this way, we can have a link budget, which is different from a radar equation, because it takes into account the propagating mode. Okay, so we did some measurement. You can see here a metal pipe, and the diameter is such that only one can propagate inside this structure. We select it because we want to limit at least the propagation at one known mode, which is the fundamental mode of the circular waveguide, which is the TE11. So we excite this field with a reader antenna. We have the TE11 propagating mode, and we include the tag inside the metal pipe somewhere, okay, at a different position with respect to the center, different bending position. You know, we did a lot of tests actually. And you can see that the tag can be used to estimate the RSSI distribution, and the distance between the two consecutive nulls is something related to the wavelength. When the metal pipe is terminated on a metal plane, metal is a short circuit. So we have a stationary pattern inside the metal pipe, and then the distance between two consecutive nulls, it depends on the wavelength. And the wavelength is not 34 centimeters, because this is the free space wavelength. This is the wavelength of the fundamental mode TE11 at the frequency, operating frequency. And we can see that in theory, the half of the wavelength is 30 centimeters, 29.6 centimeter. And we tested that the distance between two consecutive nulls is around 30 centimeters. So it means that actually it is propagating that TE11 mode. And we test it by varying the position of the tag. So we use the tag simply as a field probe, if you want. So again, some tests also with the VNA for the link budget. And it's a nice to show you that when the tag, we can use also a spectrum analyzer to see the power emitted by the reader. And for example, this is the carrier, the interrogation carrier. When the tag is activated, can reply to the interrogation, and there are 1 and 2 peaks. So with no tag response, we have just the carrier. With also we have those 2 peaks. These are a little bit shifted with respect to the interrogation frequency, and this is due to the load modulation of the chip. When activated the tag, the chip is activated and starts changing the load to modulate the backscattered signal. This modulation determines a shift of the frequency, but a very, very small shift. Okay, so it is a 300 kilohertz. So it's written in the standard. So it's a very small frequency shift. But this is needed for the reader because to extract this contribution of the tag and detect it. Okay, this is something nice to show. And we can use all those information, the power of the backscatter signal. And we can control both the interrogation power and the detected power, the backscattered power. And of course, by varying the position of the tag with respect to the center, you can see here, this is the TE11 mode distribution inside the circular waveguide, and the tag is placed in the middle, and it is same orientation of the field distribution. by varying its position so from the center to the edge. So you can see, for example, here at 8 centimeter of distance from the center of the waveguide. Again, there is the tag is vertical, but the field the field amplitude is lower, and then the coupling can be estimated 2-3 dBs less. And then if it is banded, also the field distribution is important. You can imagine that for this mode propagating distribution, an horizontal tag cannot be detected. Okay, so this is important to know. We estimate this coupling. There is still a shift between the simulated and measured coupling, but at least the normalized distribution is similar. So it means that we can use those equations, simple link budget. Again, we have some losses due to the load modulation, due to the difference between the nominal chip impedance of the datasheet and the actual. Also, the input impedance of the chip varies by varying the power illuminating the tag, because it is a non-linear circuit. Okay, so it depends also on the power. So it is not easy to predict everything. So, but at least qualitatively we can understand which is the distribution of the tag. Okay, time is over, and I have 7 minutes in delay. I want to conclude that there are a lot of applications where commercial RFID tags and reader antenna cannot be used. But we need to design antennas, and we are happy because we are researcher, and we need to find always new solution for practical problems. Please try to not to think about a problem which is not realistic. We need to solve real problems, and for example, the detection of the tags in the real environments. So. But we can imagine a lot of structure, but as a conclusion, I think there are more open problems than conclusions. So I invite all of you to think about this, and maybe we can also discuss together and propose your own solution, and maybe do some collaboration on this topic, because it's a very hot topic. RFID are widespread, and a lot of those problems, both at the reader antenna design, tag antenna design, propagating channel, how can you localize the tag, for example, localization systems over RFID tags, a lot of research activities around this topic. And I want to thank all the components of this activity, of the group in Pisa, and the operator of these activities. Professor Nepa, Professor Giuliano Manara are the full professor in my group, and Alice Buffi, associate professor on localization systems, Marcos Rodriguez Pino, University of Oviedo, Spain, because he helped us for measurement on antennas. And of course, my colleague and friend, I think he's now he's listening, and I want to thank him, because he is a very nice person, very active researcher, and he did a lot, especially for the smart glove. This concludes my talk. Of course, I'm happy to answer, if I can, of course, happy to answer to your questions, and if any, of course. This is my email. Should you have any other question, please send me an email. And I want to thank you all and the Cyan for your kind invitation.
Okay, thank you, Andrea, for a very informative and interesting session. I'm sure everyone attending the session will benefit from this in some way. So I have a few questions. I hope you will be able to, I know you'll be able to answer them. So the first one is, how was the reflected wave propagation and bandwidth performance affected with the loading method of the spiral you used at near field? So I think you showed us a spiral antenna where you had a switch and you could change the modes by changing the switch. So I think this question is related to that antenna. So the question, if I have to repeat it again, is how was the reflected wave propagation and bandwidth performance affected with the loading method of the spiral you used at near field?
Okay, let me go back.
Yeah.
Okay.
Yes.
You are asking which is when the RF switch is terminated on a 50 ohm resistor, as I mentioned also, we have no reflection back, or at least we have a small reflection back, but it is dissipated, so it is an antenna. Because basically it is not an antenna. This is a transmission line, spiral shape, and terminated. So the bandwidth is definitely larger than the UHF RFID band. But when the antennas are, the curved slot resonant antennas are excited, there is a matching lane network which is useful to split the power and to change the phase shift. But the antennas resonating at the UHF RFID band. Think that in Europe, the UHF RFID band is 865.88. So it's just 3 megahertz of bandwidth, and definitely even when the resonant antennas are activated, the bandwidth is larger. I haven't here. Let me see if I should have some backup slides. I want to see if I have a reflection coefficient, and maybe this answer your question.
Yeah.
Okay, I haven't here, but yeah, I'm sorry, I haven't S11 parameter because the bandwidth is not a big issue for this application. But I don't know if you or someone put this question, but please send me an email and I can send you some data. For example, there is a paper on this, so you can see which is the reflection coefficient, even for both the state of the antenna.
Yeah, I think the person who posted the question can mail you to discuss this further.
Yeah.
Okay, so next question is, how does a reader differentiate between two tags? For example, in a marathon event, out of thousands of participant tags, how can a reader differentiate amongst the runners?
Okay, how does a reader differentiate? Okay, I can read on the chat. Okay.
Oh yeah, that's good.
Yes. Each chip has its own code. I don't know. Okay, let me. This is all the RFID systems. Okay, you can see the slide, right? Okay, in the chip, it is stored the identification code. There are like up to 128 bits of information, hexadecimal format. And in this identification code can be used to identify a specific tag. and of course a specific object. So for example, for practical use at the supermarket, you can attach your tag on a specific object, and you can associate this identification code to that specific object. And then when this identification code is read, detected by the reader, you automatically know there is a database with a match between identification codes and the specific tag and the specific object. Of course, for sporting activities, of course, you can give one tag to each participant, okay, to each runner, for example, and you associate to each runner a specific identification code. You have 128 bits, so you can have how many combination of codes, okay? And in this way, you can detect and you can differentiate each tag. And I think that commercial readers can detect up to hundreds of tags per second. So it's very easy to do that.
Okay, thank you. So the next question is, should I read them out? I think I should read them out.
I think I can. You can read because you are the chair.
Okay. So the next question is, during SAR estimation in the hand model, whether 1 gram averaged SAR distribution has also been studied, because 1 gram SAR limit of 1.6 watt per kg is prescribed by FCC and also adopted in India.
Yeah. We focused on the European pen because we are here and we are using commercial readers which can operate only in Europe. So we referred only to the SAR limit Europe, but of course there is other specification for FCC and in India also. I think that we tested, and at least by means of simulation results, and this is also good for FCC. I mean, there is a different power limit, but more or less the amount of power is similar. By using the SAR limit of FCC standard regulation, the 1 gram SAR limit, this means that we are going to change the maximum power of the reader. But yes, I mean, this is another interesting analysis. I don't remember, I have not results for that, but it's just a matter of change the reader power. Look, if you consider the SAR limit, and you can test it and you can estimate the maximum power that we can use at the reader side. The maximum power was 27.8 dBm. But actually we used just 17 dBm of power. So it is 10 dB less. So I think this is not a big deal for practical use. Power cannot be so high to like 27 dBm, because a wearable device like this has must be as a battery, and in order to guarantee long life of the battery, we need to reduce the power as much as possible. So actually, this is not a big issue. I mean, the power limitation due to the SAR limit is not a big issue in Europe, and I'm pretty sure that this is not an issue also for FCC.
Okay, thank you. So the next question is, while designing platform-independent far-field tags, how the gain and bandwidth can be increased? Because after applying full ground, these factors are greatly affected. I think you can read the question as well. Okay.
Yeah. First of all, hello, Arti Bansal. We met in Pisa as well, and during the conference. It's hello. How are you?
I'm fine. I'm good, sir. How are you? Great to attend your presentation. It's very nice presentation. Thank you so much for this.
Thank you. It's a pleasure to meet you, to virtually meet you again. Okay.
Thank you, sir. I was encountering this problem while designing my tags. Yes, sir.
Yeah? No, please. So you are designing a platform independent far field tag?
Yes, sir. Yes, sir.
Yeah, this is a good question. I would like to have a clear answer, but typically for designing tag platform independent, we play with the electric and magnetic field distribution generated by the tag. For example, this is also good for metal, but more useful sometimes is for wearable application, since the biological tissue and actually also metal ground plane are so much affected by the electric field. Well, it's the opposite. The electric field is very, very affected by the presence of metal sheet or biological tissue. Biological tissue are dielectric materials, so they affect more the electric field. So what we typically do is create a tagged layout where the electric field is confined in the middle of the tag instead of on the edge, because if the electric field peaks are on the edge of the tags, this is more affected by the presence of the platform, even the metal plate or biological tissue. So the idea is to create a structure where the electric field is definitely they should have a ground plane, because the tag must be a ground plane, cannot be an inlay like this, for example. So it must have a ground, and the electric field must be confined inside the tag, the antenna, and the magnetic field peak can be close to the edge. These are some guidelines, but of course it depends. And you are right. You can design one tag for one specific ground size and shape, but by varying the shape of this ground, also the tag antenna performance change. So there are some guidelines, but they are not there, let's say. I would like to have a clear answer for your question, but maybe we can find it together.
Okay, sir. Thank you so much. Yeah, there is some clue there of the confining magnetic field at the edges and electric field maximized at the center.
Yeah, okay. That's some general guidelines.
Yeah, we can opt for that. Okay, sir. Thank you so much, sir. Thank you once again. Thank you, sir.
Thank you for participating.
Okay, so thank you for the answer. So the next question is, single loop configuration is quite adequate, but why go in for array configuration, which is complicated?
Because you want to extend the detection area. I can show you something. This is a single loop, two single loops with different capacitors. If you want to make it larger, if you want to enlarge the detection area, maybe you need two loops. These are concentrical loops. But for example, if you want to make it even more larger, you may have two loops, so you can make it double. The detection area is a double. So this is not a real array configuration in this. This is not an array configuration to increase the gain but to enlarge the detection area and the field distribution. I don't know if this reply and is an answer for your question.
Yeah. Okay.
Yeah, it is more complicated, of course, but in some application, maybe you can think about a shelf. The shelf is maybe large, where shelf with a book. And so if you want to cover a larger area, you don't need just one antenna, maybe, and you can have several antennas, so an array configuration. For example, in this case, you have just one port, but you have two antennas with a shared edge.
Okay, thank you for the answer. So there is another question which says that you have shown performance variations against distance between tag and detection system. So is there any performance study of the speed of the tag and the detector?
That's an interesting question. Typically, well, this is a very important, especially for. Okay, I can tell you one application. One reader antenna is attached to a train, okay, and one tag is on the ground. So one tag is fixed. The reader is on the train. When the train pass through this point, the reader can detect the tag and say, okay, I'm here. Okay, this could be one. This is one application of the RFID systems. In this case, the speed of is definitely higher than the speed of the tag. Actually, the tag is fixed in one point, specific point. Okay, in that case, we choose a specific antenna radiation pattern, because what you must do is to increase the power in order to detect the tag hundreds of meters before arriving at a certain point. So maybe you have a more high gain directive antenna toward the moving direction, and in that way you can detect the tag before, and even when you are close to the tag. Okay, so you can detect the tag before, and then you pass close to the reader to the tag, and you can detect it more. The problem is not for typical applications, because maybe the reader can be a portable handheld reader, and it is used by a human operator. So there is a speed, but it is not so high speed. Okay. So, but if the half power bandwidth of the reader antenna is wide enough, then the tag can be still detected. One very interesting problem is the phase of the tag. When the backscattered signal from the tag is received by the reader, we have not only an information on received signal strength indicator, which is related to the amplitude of the signal, but some reader we can extract also the phase of the signal with respect to the interrogation signal. So this is the difference between the phase of the interrogation signal and the backscattered. So this phase can be used for localization. So there are a lot of phase-based localization systems. In that case, the speed of the tag with respect to the reader is very important. Is very important, because the movement determines also. You can, if both the reader and the tag are fixed, the phase is a metric to estimate, for example, the round trip time, round trip distance. I mean, the double of the distance between the reader and the antenna, because this is related to the propagating mode. Okay, but if one of those is moving, there are also some further effects like Doppler effect as well. So these are specific scenarios and application as well. So the speed of the tag typically affect more on the phase instead of the amplitude. I don't know if I have answered your question, but if you want more details, please send me an email, and maybe I can give you more details, because it's not easy to give you an exhaustive answer, because this is a nice question as well.
Okay, so thank you for the answer. So, there is only one more question here, but this question I think has more to do with CST than with the actual presentation. So it says how to determine transmission power in CST. I think you can give a very good answer about this.
Well, what do you mean transmission power in CST? Because in CST we can define one lumped port, discrete port, or waveguide port, and you can set it to determine the power, or you can select a voltage port. So you are going to set the voltage of your port. You can set current value of your port, so in terms of current ampere, or a signal. In that case, you can see the power. You can set maybe the power of your impulse, okay, of your structure. So I don't know if so this is the power given to the structure. So I don't know if this is a question, or maybe it is a different question.
Yeah, I think the question can discuss it with you.
Okay.
Okay, so finally, I have a question of my own. So, see, in near field applications, we need to have the E field and the H field very. E field and the H field have to be very uniform, right? To get the proper reading of the tag. So, in order to do that, like you showed for the loop antenna, you made capacitors to make the current phase same, so that the field distribution is more or less uniform. So usually for UHF systems, the antenna size is a little larger because the wavelength and the frequency. So is there any provisions, or has there been any research to miniaturize the antennas, near field antennas in UHF RFID?
Well, all those antennas are at the UHF RFID band, and that's the problem. At the HF, so 30.56 megahertz, antennas are typically loop antennas, spiral antennas, because it's a very small frequency band, so the wavelength is so big, and the inductive coupling is used to activate the tag. But at the UHF, the problem is that the size of the antenna is comparable with the wavelength. So in that case, we have both magnetic and electric field. We have the energy distribution is not, well, in the spiral configuration at HF, only magnetic field is considered because of the nature of the antenna, which is a. But typically at the UHF, we have both electric and magnetic field for a given structure. And unfortunately, the frequency is higher and the wavelength is smaller. So 30 centimeter is not so big, okay, for a device. And So that's why we have a problem with the use of loop. We cannot use the same structure of the HF at the UHF. So that's why we need to keep the current in phase. We need to force the current to be in phase along the loop path. So I don't know if Sayan, this answer your question of
yeah, no, actually what I wanted to ask was that usually for UHF frequencies, the antennas are comparatively larger than, suppose you say, microwave antennas or higher frequency antennas. So what I'm asking is, has there been any provisions to miniaturize these UHF antennas for near field applications? I mean, some techniques to miniaturize these antennas so that the antennas are smaller than they should be in UHF RFID.
Yeah. Well, the problem is the application.
Okay.
You can do smaller. Okay, you can miniaturize the antenna. Okay, so maybe you cannot need to use a capacitor to keep the current in phase. But in a real application, for example, a shelf, think about a bookshelf. You need to cover all the shelf. So you can miniaturize your antenna, but you need to cover a specific area. So the size cannot be miniaturized. Okay. So you cannot use actually miniaturization techniques. You cannot choose different sides of your antenna structure. This is important for portable reader, for example. But for handheld reader, the size of the antenna must be very, very, very compact. So maybe in this case, you may use a loop antenna without any segmentation, without any capacitor, because maybe you know very well about portable reader, because I know you publish something about this topic. So the size is limited. So antenna is just a loop, is a solid loop, not a segmented loop, because the size is compact. But actually, portable reader, antenna for portable reader must be designed in order to get a good gain. So in that case, we have the opposite. Yeah. The antenna is very, very small, but we want to get a very good gain. For those applications, antenna must be large to cover a large area, but again, it must be used for near field application, and the field distribution must be uniform. So that's the dual. Yeah. It would be nice to use the different kind of antennas, but unfortunately, applications are leading the antenna design. We cannot choose actually antenna design. Application is a requirement. I mean, the size and the gain and the reading distance is a requirement. So that's a funny story for antenna designer.
Okay, so thank you very much for your answer. So that concludes the question answer session. So Dr. Andrea, thank you very much for a very interactive and interesting session. I'm sure we have learned a lot from your session. And I hope we can interact again in the future to host maybe another seminar or webinar. And I hope someday in the near future, you can come to India and actually give an in-person webinar, or not the webinar, then it's going to be a seminar. That would be very nice after this pandemic situation is dispersed.
Definitely will be my pleasure. And thank you again for inviting me. And thank you all for your nice questions and for attending this talk. It's always nice to share our research and our activities with others.
Yeah. So I think we can end the webinar now. Thank you, Dr. Andrea. I think you can leave the meeting, and we'll all leave the meeting and this time. Thank you.
Okay. Thank you very much. Thank you. Bye-bye. Bye-bye, guys.